Hello, everybody. Um, Welcome. I'm going to be just recording some videos, going over all the problems. Enjoy my mustache. It is a remnant of freshman retreat for those who were there, got to witness that. Um, so, let's go through this. So, I wanted to go through all the topic questions first, just one at a time, kind of give an explanation for each of them. So a student had two dilute colorless solutions, HCl and NaOH, which were at the same temperature. The student combined the solutions, and the reaction represented above occurred. Which of the following would be evidence that a chemical reaction took place? So this first one, right, on evidence of chemical reactions. Well, let's see, let's look at these. The resulting solution is colorless. The temperature of the reaction mixture increases. The total volume is approximately equal to the sum of two volumes, and the resulting solution conducts electricity. Okay, so let's kind of order these in kind of most right to least right. Not really most right to least right, because there really is only one right. But resulting solution is colorless. Okay, if I mixed two different glasses of water, right, or if I mixed water and salt water, or water and ethanol, right, aka alcohol together, and it was colorless, is that a reaction? No, right? That's not a sign of a reaction. A color change can be a sign of a reaction. In fact, a color change is often a sign of a reaction, not always. It could be simply a mixture, right? If you put red food dye in water and it turns red, that's just a mixture. Now, the correct answer is temperature, but I'll come back to that. The total volume of the mixture is approximately equal to the sum of the initial volumes. Wow. 5 plus 5 equals 10. That is surely a sign of a chemical reaction. Obviously, that one's not. The resulting solution conducts electricity. This could be a case where, again, you might look at this and you think maybe that is a sign because you see that it makes sodium chloride aqueous, right? And we know salt water conducts electricity because it's ionic. However, sodium hydroxide, right, and then HCl, like, those are both strong acids, meaning they're completely dissociated. It means they're in their ionic forms. They also conduct electricity. That doesn't really say anything. I could mix salt water, I could mix two different solutions that just mix together that both conduct electricity, right? And the resulting solution conducts electricity. Temperature changes, though, are a sign of a chemical reaction, right? They are an increase of a temperature would mean it is an exothermic reaction. And actually, HCl and NaOH is an exothermic reaction. If you combine concentrated HCl and concentrated NaOH, you need to make sure that actually, maybe we'll do this in class, in lab. You need to make sure you have it in ice, right? Otherwise, it will get very, very hot. So, a student was asked to formulate a hypothesis about what would happen if 100 milliliters of 0.1 molar NaOH was combined with 100 milliliters of 0.1 molar magnesium chloride at 25 degrees Celsius. So, if this happens, right, we have a few different options. Volume would be equal to the sum of the original solutions. Well, sorry, which of the following hypothesis indicates the student thought a chemical change would occur? Sorry. So, the hypothesis is supposed to indicate a chemical change. Don't worry about if it would or not, although it would, right? Just worry about the chemical change. The volumes are equal. Again, wow, I took 5 milliliters of water and combined it with 5, and it was 10. Surely science has happened, right? No. Um, the mass of the resulting solution would be equal to the sum of the masses of the original solutions. The law of conservation of mass still occurs. 5 plus 5 once again equals 10. Surely this is the work of a chemical reaction. No. The resulting solution will be clear. If I take water and I pour in salt water, it'll be clear. That's not a chemical reaction. This is off topic, but I do want to make sure you guys know the difference between clear and colorless. Right? They are not the same thing. Colorless means without color. Clear means you can look through. So if you have orange dish soap and you can look all the way through it and see your hand, even if it's a little distorted, right? That's clear. It's not colorless. It's orange. Right? Or like, I know, I need to grab something. Okay, I'm back. This sugar jar is green. This is a sugar jar and occasionally a vase if I don't have sugar on it and I want something nice to put flowers in. Anyways, this is green and clear. I can see through it. I can see the camera right now. I don't know if you can see my face through it. You know, I don't know how good my camera is at that, but I can see the camera. I can see the screen. Can't really read. You know, the light's being distorted a little bit, but it is green. It's not colorless. So water is clear and colorless. Sorry, that was a tangent. Anyway, the answer is precipitate. Precipitate is a sign of a precipitation reaction. Pretty straightforward there. There are times where a precipitate could form that would not be the result of a chemical change, but those are pretty extreme. You can increase, we'll cover this in our equilibrium chapter, but you can increase how much of something will dissolve by heating it up. Right? So you can cool it down and cause some precipitation. That wouldn't be a chemical reaction. But mixing two together, both at the same temperature, that's why it specifies 25, 25. Nothing weird is happening with precipitation. Nothing should be changing there. No temperature change. Right? Again, this is specifically to tell people like me who would be like, actually, temperature change, right? So there is no temperature change. There's still a precipitation reaction. All right, a student was studying physical and chemical changes. The student carried out some procedures in the lab and recorded observations. They concluded a physical change took place but not a chemical. Which could have been the result of that? A cube of metal was changed into a flat sheet. Two liquids combined, the beaker became hot. Two clear liquids combined, it became cloudy. Colorless was added to blue. It turned yellow. Okay, let's do all these going from bottom up. Because, surprise, surprise, the answer is A. Color changes don't have to be chemical changes. I was talking about before. It could be the average of the two chemicals. But if you go from colorless and blue, well, the mixture of those would be like a light blue, like a blue tinge, not yellow. There's no way you can mix blue and nothing to make yellow. So that would definitely be a chemical change. When two clear liquids were combined, the resulting mixture was cloudy. The only reason it would be cloudy, right, would be a precipitation. Again, it's possible the precipitation could come from a hot and cold, but right, one of these is very, very clearly a physical change. When two liquids at room temperature are combined in a beaker, they become hot. Right? Exothermic chemical reaction. And finally, a cube of metal was changed into a flat sheet of metal. That's just a physical change. That's just squish, right? That's like watch one of those hydraulic press videos, you know, that's a physical change. All right. How much time am I spending just on that first one? Oh, that was 10 whole minutes. Okay, I should speed this up a little bit. All right. Which of the following is net ionic equation for the reaction between aqueous sodium fluoride and hydrochloric acid? The answer is, which of the following is the net ionic equation for the reaction? Yes. So we have sodium fluoride, hydrochloric acid, NaF, HCl, right? This is actually going to be the answer here. And I'll explain why. Right? Usually with net ionic equations, we are used to something not being aqueous at the end. That's because previously we always covered things that when they were dissociating would completely dissociate, right? Or completely form a solid. We never, right, because all ionic compounds, if they dissolve, dissociate. Acids, when they dissolve, don't dissociate. And so here, F and H can form HF, which is dissolved but not dissociated. NaCl is ionic, and therefore it would be dissociated. Right, NaCl dissociated. Right, here this is just the complete ionic equation, not the net ionic, so it would be D. Equal volumes of 0.2 molar lead nitrate and potassium bromide are combined to make lead to bromide yellow precipitate. Which of the following is the correct ionic equation? This, the lead and the bromines making the lead bromide. For precipitation, it's just, right, the two halves of the chemical that's becoming the solid. All right. The reaction between aqueous strontium chloride and aqueous potassium sulfate forms precipitate strontium sulfate. Same deal. Strontium and sulfate make strontium sulfate. Well, let's keep going. We'll speed this up a bit. Or now am I going too fast? That was only 2 minutes. I don't know what to do. I'm going to run out of time. Or am I going to not run out of time? All right. Chemical change from mass change. A student places a sample of pure metal in crucible and heats it strongly. The final mass was determined after it cooled. Which of the following statements about the experiment is correct? So we go from, right, mass of the crucible is 12. Okay, so then we have really 2.4 grams to 4 grams. We have a gain of 1.6. So what's going on? Well, right, it gained 1.6 grams. Law of conservation of mass. Matter is not created or destroyed. Right. The matter can't just change, meaning something has to have been added onto it. This is a sign that something has reacted with a gas. In this case, it's oxidized. It reacted when it was heated in the air. So the mass of the sample increased, so a chemical change occurred when the bonds formed between the metal and another substance, most likely oxygen. Probably oxidation. A student mixes 20 grams of white calcium chloride with distilled water in a beaker. It was stirred until nothing was visible. After several days, all the water evaporates and white crystals are found in the beaker. Which of the following pieces confirm that a new compound has not been made? Right, if the white crystals in the beaker still have the same mass. Reason being, right, if the crystals had reacted with the liquid, they would have changed chemicals, they would have a different mass. Some of the mass would have gone with the liquid, some of the liquid's mass would have gone with the white crystals, and it would come out as either more or less. If it was a different mass, and you were sure it was dry, that could be an indication that a chemical change had occurred. Of course, that could be a little tough, because in the time it took to dry, it's possible some of it could have oxidized. Right? But if that doesn't appear to be the case, especially if you do this, let's say, a non-oxygenated environment. You do it in helium or nitrogen, something inert, and you dry it out. Right? If you still have that same mass, you know you're good. A table above summarizes data given to a student about which of the following identifies the best way to gather evidence to support the type of change. So, substance X, white crystalline solid. Mixture, clear colorless liquid. Let's look at our different things. Measuring the melting point. It's dissolved in water. It's a clear colorless liquid. Right. It is unlikely to significantly change the melting point. Adding another substance to the mixture of water and X to see whether a solid forms. Well, this doesn't really necessarily tell us what's happening, what happened when we mix them together. That would just tell us what happened after we added the new chemical. Measuring and comparing the masses of water, X, and the mixture of water and X. That doesn't matter. Law of conservation of mass, it should be the same. But measuring the electrical conductivities of X, the mixture of water and, of X, and the mixture of water X. Right. So in this case, right, a white crystalline solid, if it's dissolving, there's a good chance, right? White crystalline solid could be a ionic compound. So if we see an increased, right, an increased electrical conductivity after we add X, right, that's a good idea that an ionic solid dissolved. If we see if we measure X and it is non-conductive, and we dissolve it and it is conductive, right, that's a good indication of physical change. If X is some sort of white crystalline metal, which is usually not the case, they tend to not form crystals, and it reacts with water to make some sort of hydroxide, right, that we don't really recognize. Well, that will go from being conductive to maybe non-conductive if it's just reacted to form a new chemical, right? Especially if it gave off like hydrogen gas. So, yeah. And actually, I think I just wanted to double check that one. Yeah, that is okay. I am a little tired right now. It is almost 11 o'clock when I'm recording this, so, all right. And I've been traveling all day, so I apologize if I'm a little sleepy. That was not meant to be like, I apologize. I actually do apologize. Okay. Stoichiometry. A 2-mole sample of F2 reacts with excess NaOH. First off, always take note of this word, excess. More than enough. Stop worrying about how much NaOH there is. Doesn't matter. You have more than enough. If the reaction is repeated with excess NaOH but 1 mole of F2, which of the following is correct? You're going to make half as much. Right? You put in half as much, you get half as much. Very simple. In that case, it really doesn't matter what the actual ratio is. That's a bit of a red herring, right? If you put in half as much, you get out half as much. Here, 100 milliliter sample, 0.1, 100 milliliter sample of 0.2 were combined, precipitation. The experiment is repeated using solutions of the same molarity, which the following changes in volume will double the amount of magnesium hydroxide produced. Okay, same molarity, meaning it's a 1-to-1 ratio. If you want to double the amount that's produced, right? Double the volume. of both if they're the same molarity. If you were going with this and you want to double the amount that's that's made, right? Oh, hold on, actually. So I'm gonna make sure I'm thinking right. Yeah, pretty sure it's D, although there's, again, I am very, very sleepy right now, and I'm trying to do all the math in my head, and I'm very tired, so I'm going to come back to this one in just a second. I'm sorry. I am too tired for doing math in my head right now. Let's continue to do more math in my head. Reaction between sugar and oxygen is represented above. 0.3 moles of a CO2 was produced with 0.05 moles of that. With excess O2, the reaction was repeated at the same temperature, but this time 0.6 moles of CO2 were made. If you made double the amount, you had to use double the amount. Right, so it must have been 0.1. Let's we'll check this one. Doubling the yield. Yeah, using twice the volume of both. So twice the volume of both. Keep in mind, right? It's saying repeated using solutions. Oh, sorry. I misread this. Repeated using the same solutions, right? Of the same molarity as above. I thought it was saying of like the same molarity, like they had the same molarity of each other, right? And this is why I was confused for a second, because I know I solved the equation before. But let me show you my misread there and why I was like, hold on, now I feel like it's wrong, right? Is the way I was reading it, which is stupidly, with my sleepy dum-dum brain, would be like, okay, if they have the same, wow, this is taking a while to load. No, I don't want this. No. Is it this one? Yes. If you have 0.1 molar NaOH, and in my dum-dum brain, I was thinking it was saying they have the same molarity. So you have 0.1 molar MgCl2. Right, in this case, if it is magnesium and hydroxide that are reacting, you need twice as much hydroxide. So to get double the precipitate, all you would need to do is double this volume. But of course, right, if this is already accounted for, because you have, oh, I mixed up the ones, but you have 0.2 NaOH. Oh no, I do have that. If you have 0.2 NaOH, well, then you have to double both because they're already equal to each other. So that was the cause for my confusion there. Again, sleepy dum-dum brain, misreading things. Don't try to chemistry at 11 o'clock. This is why I tell you to go to bed. Nothing good can come from that. Alright. Silver nitrate. So, the diagrams above represent solutes present in two different dilute aqueous solutions before they were mixed, water molecules not shown. When solutions were combined, a precipitation reaction took place. Which of the following is the best particle diagram of that? The answer is going to be B. Right, we know that it is silver chloride that reacted, and we have NaNO3. First off, we have 1, 2, 3 NAs, 1, 2, 3 CLs, 1, 2, 3 AGs, 1, 2, 3 NO3s. This picture at least indicates that we have the same amount of each, equal molarities, equal amounts. When they mix, right, here we have 1, 2, 3 CLs, 1, 2, 3 AGs, and 3 combinations of these. Really, though, in actuality, these are still aqueous, which actually really means they are dissociated. But the reason this is, yeah, let me check. I just want to double check. I'm not dumb braining this again. No, it is D. Sorry, they are dissociated. Yeah. So I was saying it was B, but I was explaining the reason why it was D. Right? They're not together. They're not together like this. They are still aqueous. They are still dissociated. So they're separated like this. Yeah, so while saying it was B, I was explaining why it was D. Again, don't chemistry and tired. Oxidation reaction. When C2H4 reacts with H2, the compound C2H6 is produced as represented in the equation above. What type of reaction is this? This is an oxidation reduction reaction. All combustion is redox reactions. Generally, you can tell if something is a redox reaction if it goes from, right, I believe you covered this last year. I'm going to get into redox reactions a lot when I'm back because it's kind of big. You can tell if something is a redox reaction if you go from a pure element to a compound. Pure element, compound. That's kind of the basic way to tell. So anyways, for this one, the compound C6H8O6 reacts with I2 according to the reaction represented above. In this case, I2 starts, like we said before, as an element and ends up as an ion. In this case, right, ending up as an ion means it has gained electrons and it has changed forms. It is now, right, no longer its elemental form. Its oxidation number has changed. Again, a lot of oxidation numbers when I get back. This has been reduced. It is an oxidation reduction reaction. The hydrogens here from this are the ones giving the electrons to there. So it's not an acid-base reaction because, it is not producing those hydrogen ions as an acid giving them off. It is making those hydrogen ions because the electrons are being ripped off of those hydrogens. All right. Acid-base reactions. I'm going to go through these real quick. I was going to try and do the FRQ today. I probably still have time to do that. I'll just go quick. I'm not even going to click into these. Dissolution of HCl. Right. Down here. Which of the following pairs includes a Bronsted-Lowry base? So, includes the Bronsted-Lowry bases. So, Bronsted-Lowry bases, right, are proton acceptors. They are chemicals that will accept a proton. Going in this direction, right, the water is accepting a proton to make H3O+. A proton being a hydrogen ion, because a hydrogen ion, right, hydrogen is one proton, one electron. If it loses its one electron, it's just a proton. So H3O+, right, has formed from the base that is water. Chlorine is also a base, as it could reform HCl. It is extremely unlikely for it to reform HCl because HCl is a strong acid, meaning it completely dissociates. But, of course, completely is kind of a lie. There's always this tiny percent that will. So it is acting, right? It can act as a Bronsted-Lowry base to some regard. If anything else will, that will. FRQ titration. I'll go over this afterwards. NH4Cl and NaOH reaction. All right. 0.2 molar NH4Cl, 0.2 molar NaOH are mixed. The reaction represented above occurs. A strong smell of ammonia is observed, which following is true. NH4 is a stronger acid than HCl. Let's talk about why, right? So, a strong acid is going to give off H+. NH4 plus will give off H+ to turn into NH3. At that point, right, the water will give off the H+, force it to react with NH3 again to remake NH4. It actually is an equilibrium. It goes back and forth between these two. However, you're going to get more NH3 because NH4 is a stronger acid. All right. Particle diagram shows an aqueous solution of a weak monoprotic acid. That means single hydrogen. The white circles, right, like H2SO4 would have 2 hydrogens. That would be diprotic. And H3PO4 would have 3. That would be triprotic. The white circles represent hydrogen atoms. Which of the following shows the species that act as boron-Cid Lowry base in its conjugate acid? So, I don't know how much the video is covered. I would assume they cover it. Again, I'll talk about this a lot more when we get back. I imagine this will be one of the topics people want covered. A conjugate is a pair that go together. So, this and this here. This one has to take on a hydrogen. H2O has to take on a hydrogen to make H3O+. They're a pair. You can't get one without the other. This one just isn't a correct pair. Water doesn't give off a hydrogen. In this case, to make OH-, because here we are looking for the base and its conjugate acid. If we reverse these orders, OH- could be a base with a conjugate acid, except that OH- isn't present anywhere up here. So this could be a pair where OH- is the base and water is the acid, if it weren't for the fact that they are not present. And they have to be, again, pairs of the same chemical, just really separated by that one hydrogen to be that pair. So these first two don't count, right? Because these are different chemicals. All right, I'll come back to this FRQ after I cover these last three real quick. So, 2, right? Half reactions, these are 2 half reactions. Redox reactions are something I really want to cover when we get back. Basically, this will take more than just a little bit of time. Based on the half reactions, what is the coefficient for aluminum if the equation for the reduction equation is balanced to the smallest whole number coefficients? When we consider redox reactions, when we balance them, we need to make sure the number of electrons is going to be the same, which means each of these need to have the same number of electrons eventually. We're going to have 2 aluminums to get to 6 electrons, and then we would have 3 zincs to get to 6 electrons. In this case, in balancing them, which of the following is a balanced net ionic equation for this oxidation here? So we want 2 silvers because we need to double this number of electrons to reach 2. Right? The reason B doesn't work is because if we double the number of silvers here, we have to have double the number of silvers here. And with this one, it asks for, based on the balanced equation, which of the following identifies the oxidation and reduction half reactions? So copper here, right, is normal copper, and here we see it's copper 2+ because it's mixed with 2 1 minuses, right? We have silver with a 1- going to silver, plain old silver. We have 2 of them. When we're writing the half reactions, we ignore that. So it's copper makes 2+, silver makes 1+, right? This doesn't make sense because silver doesn't form a 2+ charge. And in this case, copper can form a 1+ charge, but this is copper 2+ because it's 2+ up there. And all of these are different variations of that being wrong. All right, I'm going to come back and do this titration here now. So, hope you guys aren't, and obviously, right, as always, these combine multiple chapters, and actually this question involves a little bit of Unit 8, which is probably why it was hard. You won't need to worry about curves until we get to Unit 8. So this is just, I kind of gave like a quick answer to that specifically because you actually don't need to know it yet. I kind of forgot that they had this when I assigned it, otherwise I would have told you not to worry about the last half. So I'll go through it from the start. I'll give the explanation for this, but really we won't worry about it till later in the year. And if it seems hard, it's because it is hard. That's actually going to be one of the harder topics of the year. Okay, in a following box, draw the Lewis diagram of HF. H. F. There we go. This is an HF molecule. An HF molecule is different from HF being an ionic compound, right? As an acid, something starts off as a molecule together, and then it dissociates and becomes ions. So that's the difference. It's not multiple ions arrayed. It's one molecule, one hydrogen, one fluorine, right? In the water, they dissociate and they become ions. So, the student performs a titration with HF and NaOH. The net ionic equation is shown above. Identify the Bronsted-Lowry conjugate acid and base pairs for above. Okay. OH is the base. Water is its acid pair. Because water could be an acid and give off an H plus to turn back into OH minus. HF is the pretty obvious acid, being that it's an acid, and it gives off a hydrogen to make F minus. If F minus took back a hydrogen, it would become HF again, meaning it is a base. So, acid, base pair. Base, acid pair. In terms of the species in the reaction, explain what occurs during the reaction that identifies it as an acid-base reaction. Well, an acid and a base react to form water. Right? When you have an acid and a base react and form water, and you have a transfer of a proton being given off and accepted by something, right? That's an acid-base reaction. At least in the Bronsted-Lowry definition, there's a Lewis acid, and a Lewis base definition, which has to do with electrons instead of protons. We aren't really going to cover those this year, so don't worry about that. But if you see Lewis acid and Lewis base, that's just an expanded definition. It also covers this, right? In the case where a base is an electron donor, and OH minus is donating an electron to H plus to get it to like react, right? Let's not worry about that now. The equation can be written in particulate form using the key, draw the correct products above their formulas. All right. This one's just the black circle. That one is, right, the white circle with two small white circles. That one should be pretty easy. All right, real quick with these ones here. I'm not going to spend too long on here. How many moles of HF are in 30 milliliters of 0.15 molarity of HF? This is just, all right, solution chemistry. This is just calculating molarity. So 30 milliliters, that can be, right, 0.03 liters, right? 30 divided by 1,000 multiplied by 0.15. So just do, right, 30 divided by 1,000 times 0.15, get 0.045 moles. Draw an X on the horizontal axis to show the amount of NaOH that has been added when the equivalence point has been reached. Okay, this is the part we haven't really talked about because that's chapter 8. Start again. Equivalence point is when the reaction itself is done, when you've added everything, and that forms a big straight line. It shoots up in pH here because any additional NaOH you're adding just makes the pH rise. It's no longer slowly reacting with the H+, kind of like fighting to slowly change it. So right here, this is called the equivalence point. All right. On the same graph, draw the curve for the titration of 60 milliliters of HF with 30.3 molar NaOH. All right. If you have 60 milliliters of HF, you're just going to have more HF, which means you have more H+, which means you have a higher pH, which means, you have a more H+, which means you have a lower pH, so it just starts off slightly lower. And it goes, right, instead of going to 15, right, because the NaOH is twice as strong, instead of going to 15, it would have to go to 30. So it would be like, whoa, right? It would like slowly rise like that, kind of in the same shape, just like basically bring this down a bit, elongate it so that this spikes up at 30. That's all. That's not really something you would know until Unit 8, so don't worry about it. All right. We're at around 40 minutes. I'm just going to cut it off here because I'm going to assume there's some stuff, you might be doing attendance stuff, getting ready at the start, so yeah, have a good one.